In this example problem, we're going to create a deflection versus time plot for the first 20 years of this cantilever beam with a distributed load. Our dead load is going to be the self-weight, and our live load is going to be 1.2 kips per foot, with 0.4 kips per foot of this live load being sustained on our beam. Our section is shown here, with 4 number 9 bars in tension and 3 number 8 bars in compression, 21-inch depth and 14-inch width. And we're told that immediately after the forms are removed, the beam is subjected to dead load and the sustained live load. So that's our immediate loading, and this is for 10 years. Then the rest of the live load is applied and remains on the beam. So we'll have 4 different deflection components, 2 short-term components, which we'll call delta 1, and delta 3 is going to be another short-term, and then 2 long-term components, which will be delta 2 and delta 4. So the first thing that we need to do is calculate our self-weight. So we'll do that by taking our base width, 14 inches, times height, 21 inches, divided by 12 inches per foot squared, and then take this times 0.15 kips per cubic foot, which is the density of our concrete, our reinforced concrete. So then we'll get our self-weight to be 0.306 kips per foot. We'll next calculate our I gross. So our I gross will be 14 inches times 21 inches to the third divided by 12 will give us an I gross of 10,805 inches to the fourth. We can next calculate our M cracking. So our M cracking is our FCT, the tensile strength of our concrete, 7.5 roots, F prime C, 3,000 psi. Remember, ACI expressions, we use psi under our square root, times 10,805 inches to the fourth, which we just found, divided by our YT, or the distance from the centroid to our extreme tension fiber, so 21 inches divided by 2, and then I'm going to convert things into kips, so we're going to divide by 1,000 pounds per kip to give us an M cracking of 422.7 kip inches. So we next need to find our cracked transformed moment of inertia. So to do that, we need to first find the depth of our neutral axis KD. So we'll find our EC, which is 57,000 square root of F prime C divided by 1,000 pounds per kip will be 57,000 times 3,000 psi, which will give us 3,122 KSI. We can then find our modular ratio, which is 29,000 KSI divided by 3,122 KSI, which will give us an N of 9.3. We next need to find our KD, and we'll do that by summing our areas above the neutral axis times the distance from the neutral axis to the centroid of that area, and set it equal to the areas below our neutral axis times the distance from the neutral axis to the centroid of that area. So we have 3 areas. We have the uncracked concrete, 1, and the distance from the centroid to the neutral axis for 1. We have our compression steel, our transformed compression steel, and the distance from the centroid to the neutral axis for 2. So that's above the neutral axis. And then below we have just our transformed steel, and then the distance from the centroid the neutral axis 3. So I did this for us. B times KD is 1. N minus 1 AS prime times KD minus D is 2. And then N AS times D minus KD is 3. So we can plug in all of our values now. So we know our B is 14 inches divided by 2 times KD squared plus 9.3 minus 1 times our AS prime, which we have 3 number 8 bars, times our KD minus our D prime, 2.5, plus, equal to 9.3 times our AS, which we had 4 number 11 bars, 1.56, and then times our D, which is 18.3, minus KD. So we can see that this is going to be a quadratic, so I'm going to simplify things in terms of a quadratic. So we'll have 7 KD squared plus 77.7 times KD, and then minus 1,011 or 1,111.2, and this is equal to 0. And we can solve this, and we'll find our KD is equal to 8.22 inches. We can use our KD and our parallel axis theorem to then find our I crack transformed. So our I crack transformed is going to be the summation of our different areas, the moment of inertia of that area, plus the area of that area times the distance from the centroid of that area to the neutral axis squared. So we'll have our area 1, our area 2, and our area 3. And for our steel areas, we're going to neglect the moment of inertia of the steel itself and just consider the AD squared component. So you can see we have our component 1, our AD squared component for 1. We have our AD squared component for 2, and our AD squared component for 3. So now plugging in our values, we'll have our B, 14 inches, times 8.22 inches to the third divided by 12, plus 14 inches times 8.22 inches times 8.22 divided by 2 squared, plus our n minus 1, so 9.3 minus 1 times our AS, 3 number 8 bars, or AS prime, times our KD, so 8.22 inches minus D prime, 2.5 inches squared. And then our last component, our AS 9.3 times 3 number 11 bars times D 18.3 minus 8.22 squared. And this will give us an I cracked transformed equal to 9,132 inches to the fourth. Our next step is going to be to find the immediate deflection under the dead load and the sustained live load. So we'll take our 0.306, which was our dead load kips per foot, plus 0.4 kips per foot, which is our sustained live load, times 18 feet squared, divided by 2, and then times 12 inches per foot to change our units into inches. And we'll get a moment here of 1,373 kip inches. We can then find our I effective. So as we did before, we're going to find our M cracking over MA1. So our M crack, 422.7 kips or kip inches divided by 1,373 kip inches gives us a ratio of 0.308. And then we can find our I effective under this loading. So 0.308 to the third times our I gross, which was 10,805 inches to the fourth, plus 1 minus 0.308 to the third times our I crack transformed, which we found to be 9,132 inches to the fourth. And we'll get our I effective here to be equal to 9,181 inches to the fourth. We now can find our deflection under this loading. So our deflection is going to be our total load, 0.306 kips per foot plus 0.4 kips per foot times 1 foot divided by 12 inches times 18 feet times 12 inches per foot to the fourth divided by 8 times our modulus, 3,122 KSI times our I effective, which we just found to be 9,181 inches to the fourth, which will give us a deflection here of 0.559 inches. So this is our immediate deflection caused by our dead load and the sustained portion of our live load. We're now ready to find the long-term deflection that's caused by the dead load and the sustained portion of our live load. We'll do this by taking the immediate deflection that we found in the previous step times a lambda factor, which accounts for the long-term effects of this loading. So our lambda factor we can find by knowing our C factor and our rho prime. So our C for a t of greater than 5 years is equal to 2. So that'll be easy to plug in, but we need to find our rho prime. So rho prime is our compression reinforcement ratio. So we'll have our 3 number 8 bars, so 3 times 0.79 square inches, divided by our B, which will be 14 inches, times H, 21 inches, minus our D prime, 2.5 inches. And this will give us a rho prime of 0.009, 0.9%. So we can then plug these in to find our delta. So our delta 2 is equal to 2.0 divided by 1 plus 50 times 0.009, which will give us a lambda 2 equal to 1.372. And we can then find our delta 2 to be equal to 1.372 times our deflection from our previous step, 0.558 inches. So we'll get our deflection here to be 0.766 inches. So this is our long-term deflection caused by the dead load and the sustained portion of our live load. We're next going to find the immediate deflection caused by the additional load, where our additional load is the non-sustained dead or live load, so the additional 0.8 kips per foot of our live load. In order to find this deflection, we'll need to find the total deflection caused by both the dead load and all of the live load. And then we'll subtract out the deflection, the immediate deflection that we found before from the dead load and the sustained portion of the live load. So our first step is going to be to find the moment under the total load. So our total load here is going to be 0.306 kips per foot plus 1.2 kips per foot times our length, 18 feet squared, all divided by 2, and then times 12 inches per foot to give us units of inches, which will give us a moment of 2,928.2 kip inches. We'll then find our M crack over MA. So 422.7 kip inches divided by 2,928.2 kip inches is going to give us a ratio of 0.144. So we can then find our I effective. So plugging in our 0.144 to the third times our I gross, 10,805 inches to the fourth, plus 1 minus 0.144 to the third times our I crack transformed, which is going to be 9,132 inches to the fourth. So this will give us an I effective of 9,137 inches to the fourth. We can then find our deflection under this total load, which is our dead load plus our total live load, 1.2 kips per foot. And then we're going to change this into inches, and then times 18 feet times 12 inches per foot to the fourth, and then all this divided by 8 EI. So 8 times E, 3,122 KSI, times our I effective, which we just found 9,137 inches to the fourth. And we'll get a deflection here of 1.197 inches. Our delta 3 then, or the deflection due to just the additional load, will be this deflection that we found, 1.197 inches, minus the immediate deflection caused by the dead load and the sustained portion of the live load, which we found to be 0.559 inches. So this is going to give us a delta 3 of 0.638 inches. So this is the deflection caused by the immediate deflection caused by just the additional live load that wasn't considered before, and the additional live load being 0.8 kips per foot. Our final deflection component is going to be the long-term deflection caused by that additional live load that wasn't considered before, so the additional 0.8 kips per foot. And this we found the immediate deflection caused by that 0.8 kips per foot was delta 3. So now to find the long-term deflection of this additional component, we'll just take lambda times that deflection that we found in the previous step. Because our AS prime, so our compression steel is the same for step for our step 2 and this step, and because our T is greater than 5 years, this load being applied at 10 years and us looking at 20 years for our final deflection, so T greater than 5, which means our XC will be the same. We know that our lambda 4 in this step is going to be equal to our lambda 2 from before. So that means that we can just find our deflection, delta 4, equal to our lambda 4 from before, which we found to be 1.372, times our delta 3, which will be 0.638 inches. So this will give us a deflection then of 0.875 inches. And this is the long-term deflection caused by only the additional or the remaining live load that we didn't consider before. We can put it all together now and find the total deflection. So our total deflection is going to be the sum of all our different components. So our immediate deflection under the dead load plus the sustained portion of the live load was 0.559 inches, plus the long-term component of this loading, which was 0.766 inches, plus the immediate deflection of the additional live load that we hadn't considered before, 0.638. And then we're adding on the final long-term portion of this loading, which we hadn't considered before. So 0.875 inches to give us a total deflection of 2.84 inches. So this is our total deflection, and we can plot our load versus deflection then, and we'll see we have our immediate deflection due to load 1, our long-term deflection due to loading at 1, and we have our additional immediate deflection due to the additional loading at time 1, and the additional long-term deflection caused by that additional loading. So part B of our problem wanted us to see if our beam meets the deflection checks for structures supporting sensitive elements. So our deflection check includes the long-term deflection from the immediate sustained loading and the immediate deflection of any additional loadings. So we're going to look at our delta 2 plus delta 3 to see if our deflection checks are met. So our delta 2 we found to be 0.766, and our delta 3 we found to be 0.638. So we found this to be 1.4 inches. Now we'll compare this to our L over 480 limit. So our L here is 18 feet times 12 inches per foot divided by 480, which in this case is going to be 0.45 inches. So we can see that our deflection is greater than the deflection limit. So we are no good. If we were designing this beam and this structure to support a sensitive element, we would need to make the beam deeper in order to make it stiffer so that we could limit our deflections.